Well, so today we'll discuss the Vana modules. This is slightly advanced topic. So the irreducible representations of a simple groups are characterized by their highest order state. And you know the highest order states gets annihilated by the raising operator. But in physics, we usually deal with lower lying states. I mean, not always the highest order state, but the states that has been generated from the highest order state. Not all of them will be useful, but only some low lying states. Okay, so for that, the following machinery is useful. So the idea is basically that if you have the highest order state and then you operate the lowering operator again and again repeatedly, okay, and then you consider all possible states. So it may be sometimes tedious when you look for some very high dimensional representations. You start with that. Okay, so that's why these HANA modules may play a crucial role to avoid that tedious task. So in this context, we have to remember also the number of lowering operators equal to the rank of the algebra. So that we have already discussed this thing. And their repeated actions or highest state generate all the low-lying representations. Right? Another question that we want to address is how to single out the irreducible representations that we are interested in. Okay, instead of constructing all possible irreducible states, how to single out the irreducible states that we are interested in. So Verma module construction does that job. Okay, that's why we are focusing that thing. Now here we will define something which is called the Verma. So the Verma lambda or the highest state is defined as it's like a collection of infinite number of states obtained by repeated application of lowering operators to a highest state lambda. And if you want to collect them, this ensemble is called the Verma. Okay, and this lambda get vector of the state is the residing on or inside the Weyl chamber, and that's what we have seen already repeated times. Now consider the SU2 Verma module associated with the highest order state with density level 2, right? Because twice times the spin projection. It's like an integer 1, so it's like 2. Now the SU2 has rank 1, so that there's a number of lowering operator, this will be only 1, T minus. The full Verma module is constructed by repeated action on 2, unless you hit something where you get 0. Right? So Verma 2 we define like a collection of states like 2, 0, minus 2, minus 1, so on. Now the question is it like an infinite number of elements will be there or what? If you do this task and if you follow the action of this raising or the lowering operators, then you see this 2 minus 2k, the state is related to as like t minus to the power k 2. That means if the t minus is repeatedly act on this state 2 for k times, then you get this state. So then we are free to apply t plus operator to any one of those states, right? So t plus acting on the minus 4 is basically t plus this acting on this, and then this will be like a t minus cube 2. If you use this formula, you can see this thing. And this is basically 0, because this is the highest order state. So the t minus cube 2 is the actual highest order state. So here the Verma 2, we can write it down like a 2, 0, minus 2 is like a collection of triplet kind of thing. And the GH sum of Verma minus 4, and which is cannot be further reduced or lowered on that way, right? So this actually form a three-dimensional irreducible representations. And as we can further notice that t plus acting on this 2 minus 2k, we can write it down in this particular commutative form. And if you compute that, you'll get k times 3 minus k at 1 state. So this vanishes for k equal to 0, 3. So that's why the Verma minus 4 is singled out, right? So in the absence of first three states, we obtain another Verma module with a state of highest weight with negative Dimitrov index, which contains no other state of highest weight. So this is the way we can single out the state, and that's the idea of the Verma module. So now the next question that we want to ask is, what do the states 2 and minus 4 have in common? So let's consider a rank R algebra and form its Verma module associated with its highest weight state lambda, which is defined as the rank or the algebra is R. So we have some R elements will be there, A1, A2, so AR. and which are of course in or on the walls of the Weyl chamber, right? So thus this t plus I actually acting on this lambda is basically 0 because it's the highest state for all possible choice of i's 1, 2 are. Then the worm will be like a collection of all possible states that you can generate, right? So t minus I1 acting on n1 times, t minus I2 will be acting on n2 times, and t minus I acting with the nth times, and so on. And for all im equal to the 1, 2 r, because this will be like one element, the second element, and the nth element, and so sorry, rth element, and so on, because the r elements are there as we have noticed here, right? So now among these infinite states that lie in the irreducible representation leveled by this lambda and more. So since the effect of t minus I is to subtract the simple root alpha I, the Verma model consists of the states like mu, which is basically lambda minus ni alpha I. So that means basically it is acting on the at times, basically the ni is how many times it is acting. So every time you basically subtract the alpha I, right? So ni times this alpha I. If you can think like a you act n1 times this thing, n1 alpha 1, n2 alpha 2, and so on, that you will get the the Verma module states. This is a collection of all those states. So now, of course, this ni has the positive integers or 0. That tells you that either this t minus is acting or is not acting for that particular element. Now, since the lowering operators don't operate in any pre-assigned order, their commutator generates all possible lowering operators associated with the positive roots also. For example, like SU4 has 3 lowering operators, right? Because the rank is 3, but their commutator generates 3 more lowering operators, right? So this enables us to construct a particular weight in multiple ways. Okay. So this multiplicity of a weight mu in Verma lambda is basically defined as n lambda, and is not power like caption, it's like index kind of n lambda mu is equal to the number of ways this lambda minus mu can be expressed as a sum of the positive roots with positive coefficients. Okay, so that gives the multiplicity. How many ways we can express? Now, in order to determine the multiplicity, it is convenient to introduce an operator. Okay. Such that associated with the operator, we can identify those numbers. So let's associate to any state nu an operator e nu. Okay, and that satisfies this thing that e lambda e mu equal to e lambda plus mu. Okay, you can think like this, like an exponential operator or map kind of thing for any two weights lambda and mu. Now we'll define something called the constant counter. Okay, so introduce a constant counter, which is like a product over the all positive roots 1 by 1 minus e alpha. Okay, well, alpha the positive roots. For example, like if you consider the SU3, you have 3 positive roots. So alpha 1, alpha 2, and alpha 1 plus alpha 2. So you basically see constant number is basically defined in this particular way. Now for a given Lie algebra, rank r and dimension d, it will be the product of n minus r by 2 terms, and that we have seen already, right? So this one, and now we can define this 1 by 1 minus e minus alpha 1 in this Taylor series, and we can write down the power exponential like 1 minus 1 plus e to the power minus alpha 1 plus e minus 2 alpha 1, and so on. Okay, so then constant number you can write it down. If you recurse this relation, then 1 plus sum over mu n mu e mu, right? And what is your mu? Mu is basically ni alpha I, okay, that we have seen already, and ni are the all positive integers or 0. This is the generated from the axiom of the Ti. And n mu simply counts the sets of sums over the positive roots, and that yields mu. Now, for example, if you consider SU3, we write it down like C equal to constant counter like 1 plus e minus alpha 1 plus e minus alpha 2 plus twice e minus alpha 1 minus alpha 2, and so on. Now you'll be wondering, here the coefficients are 1, what is 2? Since there are 2 linear combinations of positive roots, that yields that combination, right? So 1 by adding alpha 1 and alpha 2, so you get alpha 1 plus alpha 2. Another, in the alpha 1 plus alpha 2 itself is a positive root. So that's why you have 2 possibilities to reach out to these configurations. That's why this n mu is 2. In this way, you can understand, right? So this is the multiplicity, how to count down this thing. So now C is closely related to the Weyl functions. So the Weyl functions Q is defined as the product of these positive roots e to the power alpha by 2 minus e minus alpha by 2. So where you can take out this e alpha by 2. Now, while taking out the e alpha by 2, what is this? What you get? You get a, while taking out outside the product, it will be like e sum over alpha over the positive roots by 2. Now, we know sum over the positive roots is nothing but the row, right? So that's why we define this thing. Remember the Weyl vector, which is the half the sum of the positive roots, right? So that's why e row you get, and then you get the sum product of the positive roots 1 minus e minus alpha, and this is nothing but the inverse of the constant number. So now you can see how the constant number and the Weyl functions are related to each other through this Weyl vector. Right. So now we define the formal character over the Verma modules. Right. So the chi is represented the character. So Verma module character chi is defined as n lambda mu e mu over this all these mu weights actually. That's sum over the all the weights in the module. Okay. So you can write it down chi verm lambda equal to constant number times e lambda. Okay. And then it follows from there that q chi verm lambda equal to q c e this thing, and then we know how this q and c are related. We transform that, and then we get e use the property of the e operator. So e lambda plus rho, and that's the thing you can easily derive. Okay. So now again we can ask the question that how we can split up Verma module into irreducible representations. So we have noted that for SU2, a state T minus Q 2 state 2 is annihilated by T plus. So in order to identify such states in a general Verma lambda, consider a quadratic Casimir operator C2 somewhere a TR. So R is the representations. Okay. So that commutes with all the elements of Lie algebra. You know that's the property of the Casimir. So C2 is commuting with the TRA. Again, C2 equal to, from the basic definition of the Casimir, you know, using this metric, we can define like Gij, Hij, sum over alpha, where alpha the all non-zero roots, E alpha, E minus alpha. So now split the sum over positive and negative roots and use for positive roots only. That E alpha acting on the highest state equal to 0. Now, if we have this equation and this is think of as like an operator acting on the highest state lambda, okay, so that we can write down the same thing but in a commutator form, because the one term E alpha acting in this thing will be 0. So this is identically satisfied. And then we further simplify this thing, use the property of this Hi acting on the highest state, is the definition of rho and all those things, we can write it down in this particular form. So by completing the squares and using the inner product defined by the killing form that we have learned earlier, so you can write it down this way. So since C2 commutes with all the generators, its value is the same for any state of the Verma module, right? So it doesn't matter whether it's a lambda or mu. So you replace this lambda highest state by the mu. So that's what we find this thing. So now, if mu k is the highest state in Verma lambda, we have C2 acting mu k equal to mu k plus rho plus mu k plus rho inner product, and then rho inner product acting on the state mu k. So this lambda, this hash word is mu k, so it's replaced by the mu k. Now for highest state, you know, lambda plus rho inner product is mu k plus rho inner product, right? So as they have the same length, this lambda plus rho and mu k plus rho are related by Weyl transformation, right? The inner length are same, so that they are related by the Weyl transformation, because Weyl transformation preserves the length. For example, like for SU2 Verma module, this rho equal to 1, the two highest states yields as 2 plus 1 equal to 3, and then minus 4 plus 1 equal to minus 3, which are indeed on the same Weyl orbit, because the 3 and this is minus 3. So that's why explicitly you can see that is related by the Weyl transformation. Now this singles out a finite set of weight state mu k, where k runs from 1 to n, and each standing at the top of an irreducible module, irreducible mu k, which contains no other states annihilated by the creation operator. Okay. So in SU2, there are two irreducible modules. One is finite dimensional with its highest weight in the Weyl chamber, and the other is infinite dimensional with its highest weight outside the Weyl chamber. Right? So Verma modules split up as finite sums of irreducible modules. all are infinite dimension except irreducible lambda. Now, next step is to define a Verma module for each mu k and express it in terms of irreducible module contained within the Weyl chamber. Yeah. So to do so, we order the weights mu k inside the Verma module lambda so that mu1 is the longest weight, mu2 is the second largest weight, mu2 is the second largest, and so on. So it's like a lexicographically you just order that thing. The relation between Verma and the irreducible characters are basically chi Verm equal to chi irreducible plus aj mu k chi irreducible, where the j less than k. Now this chi irreducible equal to basically your n to the power k lambda e in small lambda, where this implies basically the number of states of weight lambda. Okay, and then you just simplify that thing and you find out this relation. And then again you multiply by this q on both sides. From there you write it down in this particular way. Okay. So now the character is invariant under the Weyl transformation, since the irreducible transformations are a collection of weights on the Weyl orbits. Now Weyl functions transform under Weyl group, which is basically a simple reflection Ri, will permute the positive roots into other positive roots, except for the simple root alpha I, which goes into its negative. That means Ri is act on this E alpha by 2 minus E minus alpha by 2 as minus of E alpha by 2 minus E minus alpha by 2, and it changes Q as minus Q. So for any element omega of the Weyl group, changes as Q omega changes the Q as Q act on like minus 1 to the power L function of omega Q, where L omega W is the number of reflections in the Weyl group element. So how many reflections, like a Z2 kind of thing, how many reflections you get, right? So from there you use those equations and you derive this relation. Okay. So where omega or the W mu k plus rho is the Weyl image of mu k plus rho. Thus for any W or the omega that belongs to the Weyl group element capital W equal to, you can write down in this particular format. You can just do some little bit of algebra and you can get these relations, and which holds for all elements of the Weyl. Now this implies that E mu k plus rho is basically goes as like E omega lambda plus rho for some Weyl group element, right? Because Weyl group element act on this mu k plus rho, as mu k is basically the same as the the lambda for that thing. So it follows that Q chi irreducible equal to minus 1 to the power L function of omega E omega lambda plus rho, as long as that all weights of the form mu k plus rho are on the Weyl orbit of lambda plus rho. That's when it will be true, right? Now to see that, assume the existence of a state mu m plus rho which is not on the orbit of lambda plus rho. Let's assume that. By repeated applications of Weyl transformations, we arrive at a new state in the Weyl chamber or on its wall. This would imply that both this state and lambda plus rho live in the Weyl chamber. Right? So it is possible to show that with the same length and differing by sum of positive roots with positive coefficients, they must be equal to one another. For example, let's consider delta as a difference. Okay, lambda minus mu m be their difference and write down as 0 equal to this thing. And then you can rewrite and do some little bit of algebra, and you can write down in terms of inner products. The inner products will be greater than equal to 0. Since it is assumed to be in the Weyl chamber, so this will be greater than equal to 0. Hence, it can only be 0. Okay, when this mu and m equal to 0. Thus, the two states are same, and Q chi equal to write down in this particular form. Is that actually the exact equation, right? So now from that equation, you can write down chi irreducible character equal to minus 1 to the power L omega E omega lambda plus rho minus 1 to the power L omega E omega rho, and this is nothing but this famous Weyl character formula, and which we will be using later. And as for lambda equal to 0, Q is given like this. So that's why the denominator factor out like this problem. Now, how we calculate the dimension for given a representations which represent by some level? What is the dimension? How we calculate? The dimension of the universal representation is simply the character with the operator e replaced by 1. Okay, but it sounds very trivial, but it's not like that. Thus, for any weight mu, we define epsilon mu in terms of p lambda, where exponential mu lambda t. But t is some real parameter. Then the Weyl character formula you can write down in this particular way, where a is defined like this, and then the epsilon mu you write down expressing this thing. As the Weyl transformation don't change the length, so this will be the same thing, right? We just inverse the operator kind of thing. After summing over omega prime equal to omega inverse, we obtain this relation. I put it like a homework to find out this thing. Hence, we find out epsilon rho a lambda equal to epsilon lambda a and rho, and then you can express them in their product form. Now, expanding about t equal to 0, you can write down in terms of t to the power n, product of all these positive roots, lambda, alpha, inner product, and so on, all the terms, where n is the number of positive roots. It follows that epsilon rho function of this thing is related in terms of the product like this, and the order p elements. Now, setting the t equal to 0, you drop out these terms and then equate the left hand side equal to right hand side and set this p equal to 1. And then the Weyl dimension formula is like a dimension of the universal representation is product of all these alpha greater than 0, all these positive roots, and the 1 plus lambda alpha inner product divided by rho alpha inner product. And this is a convenient way to find the dimension as a polynomial in the Dimitrov levels of the highest order state. Now, for example, like in SU4, what you can find out that there are 6 roots, right? 6 positive roots. The dimension of the representations, what you label as A1, A2, A3 is like a 6th order polynomial. So you write it down like 1 plus A1, 1 plus A2, 1 plus A3, 1 plus A1 plus A2 by 2, 1 plus A2 plus A3 by 2, and then 1 plus A1 plus A2 plus A3 by 3. And that's the dimension, you get this thing. Now, what are those corresponding positive roots? So you get those states, fundamental states like 1, 0, 0, 0, p, then 1, and then 0 to the point minus and so on. So you get 0, 1, 0, and 0, 0, 1, all these things, and then you add alpha plus alpha, you get 1, 1, 0, so you get 1, 1, 0, and then you add this thing, so you get 0, 1, 1, and then you add all these 3, so you get 1, 1, 1. So you get basically this structure, right? So in this way, for a given state, which is labeled by the Dimitrov level, this thing, using this dimension formula, you can understand what is the dimension associated with those Dimitrov level, and that you can calculate by yourself. Right? Good.